This is Lab 6, where we will be implementing matrix multiplication and Hamming codes. Our lab is split into two parts. In part B, we will be implementing matrix multiplication, and in part C, we will be implementing Hamming codes. The first thing we need to do is write in our matrix.h file, so we can declare our function, which is void multiply ax, and the float pointer is our array. Integer n is one dimension, and integer m is the other dimension, and this is another pointer to y. So we can copy this function declaration into matrix.c file, where we can copy that function declaration, and we have to include matrix.h. So how multiply ax works is it computes the product of y equals ax, and where a is an n times m matrix, and x is a m times 1 vector. And y is the output, which will be an n times 1 vector. So an example would be a 4x3 multiplied by a 4x1 to get another 4x1. And here's the equation to get that. So that is what our function has to do. So to begin in our function, we need to keep track of what row we're on and what column we're on. And to do that, we can use a nested for loop and counters. So we can declare our row and column counters. So we can start our for loop the usual way, which is row, which starts at 0, and row is less than m rows, and we increment to perform the task again. The same is for the column portion, so this will be a nested for loop. For the rows portion, we want y at row to be initialized to 0 because it is the sum, so we need to start it at 0. So this is the row summation. So for columns, this is essentially performing a times u, and then b times v, c times q, and d times z. So y at row is plus equals a at row times n columns plus columns times whatever x at columns is. So this equation is formed to make sure we are selecting the right part of the array. So now we can run the code, compute, and check the results, which we can see is correct. So basically our matrix multiplication works by knowing this is a single dimensional array, which is to multiply row by the size of each column, which works because in an array the index starts at 0. So by adding columns, this makes it a single dimensional array. But since we verified part B, now we want to use it in part C for Hamming's code. So we do the same thing, go into our part C headings file where we declare our functions. We called it multiply hx for Hamming's, and we aren't using floats, but we're using integers. Then we can go into our matrix.c file for part C, and we can use the same algorithm we use for the multiplication of matrices, except we need to copy our function for it. And we also need to do, what we need to do is y at row mod equals 2. So in part B's main, it prints the results, but here we will make a function that prints the results, which is what we call show mult. This function will show the results. So we can borrow the code in part B's main to do this. So same format, nested for loop, and print out the results. But we can also implement an error, which is this statement. So if row is less than n columns, which essentially means if we go through all the columns and row is less than n columns, that means there's more rows to print in y. So here we only want to print that row in x, which is this line, else we are going to print the closing bracket. So we can go into our main and write the Hamming's code, where we include our IOs and our matrix.h file. So we can declare our Hamming encode, our Hamming decode, and we also declare the rows and columns of our encode and decode because our matrix multiplication needs to know the dimensions of the matrix. So this is the message to send, this is the resultant, and this is the syndrome. This is the error syndrome. It's all 0 if there are no errors. So 1 would mean that there's an error. So first we perform our Hamming encode and show our results, which is here where we print which is why we call the show mult function. Then we want to do the opposite and do the decode portion, which is essentially the same as encode, but we use the resultant and multiply it by the decode, then we receive the syndrome. So now we can print it and show the results, which is here. And finally, we want to show the bit error at the receiver. So R at 1 is now 1, which introduces an error in the second bit. And we can do the same computation. So we can copy the above again because we want to do it over again, which will show the effect of the error. So we can run the code. And first part is no bit error, which is correct. But for the second part, we can see that the decode syndrome is now 101, which shows that the second bit was the one with the error. And that is Lab 6.